So let's look at, so maximum voltage swing then, as we said, is determined by these two considerations. V0 is less than or equal to ICQ RE parallel RL, and V0 is less than or equal to either this term here, VC sat, or VBE here. Okay. Now, if you note, so let's look at these two terms. Suppose that this is important and this is important here. So if we look at these two terms here, we note the following: that as I increase my ICQ, what happens is this term goes up, this limit goes up. On the other hand, this particular limit goes down. Okay, and similarly, something similar happens with RE also. Okay, so what happens is, as you try to improve this limit goes down, or as you try to improve this limit, this particular limit goes down here. And therefore, the optimum condition will be that the two limits are the same. Optimum condition for ICQ-RE, optimum biasing would be when this limit is equal to this particular limit here. Okay, so that's the optimum condition, when the two limits balance each other. So we have VCC minus VB minus ICQ-RE is equal to ICQ-RE parallel RL. So we have this condition for getting maximum swing in my common collector amplifier here. The condition over here. The rest is, of course, algebra here. You rearrange and you get an expression for ICQ for getting maximum swing here. And once you get an expression for ICQ, then you get an expression for V0 as well here. All right. So the idea is we have two limits on swing. One is given here, determined by the current drive capability, and the other one, either this or this. I'm taking this one as the limit here. The other one coming from the fact that base voltage cannot exceed the power supply voltage here. So we have these two, balance them together, and you get the condition for maximum swing, which is given over here. Okay, and so this is the then the condition here. You need to bias it in this particular manner, and when you bias it in this particular manner, you get a maximum swing, which is shown over here. So the way to proceed then in design is, let's say you're given a VCC supply voltage, and you're given an RL. So VCC and RL are known to you, and what you have to do is design the amplifier for a particular value of V0. So you are looking for a certain V0, let's say, and once you decide how much V0 you want, that V0 along with VCC, VB, RL, that will give you a value of RE. Right? That will give you a value of RE here, and once you have a value of RE here, you get a value of ICQ here. So that's how you end up getting the value of RE, and you end up getting the value of ICQ here. Okay. Now, to get the best possible swing for a particular VCC and particular RL, you can note from this expression what you need to do is make RE much smaller than RL. If you do that, RE much smaller than RL, you can get a swing which is VCC minus VB by 2 here. Okay. But the price, so for example, if I have 12 volt here, this is 0.7. So 12 minus 0.7 is 11.3 divided by 2. So roughly 5.6 is the maximum swing that you can get here. But note, what you have to do is make RE much smaller than RL. And when you try to make RE much smaller than RL, what happens is, note that the bias current depends on RE. And therefore, as you make RE small, what happens is the bias current becomes very large, and you end up getting high power dissipation. So we'll see that with an example later on. All right, but this shows you how to design this particular amplifier for a particular swing that you may be interested in. The closer you want the swing V0 to the maximum value, the smaller RE will have to become, and the larger the bias current of this amplifier. Okay, so this particular example will show you here. In this case, we have biased it at 3.4 milliamperes. So, depending on R1, R2, and RE, we have a bias current of 3.4 milliamperes. VCQ is 6.5. And note, these are the usual values of gain, input, and output resistances here. Swing we get is 3.2. Because we have biased it at 3.4, we get a swing of 3.2 here. And in the next case, we have biased it at a much higher current, which is 25 milliamperes here. That's why you see all the resistors are smaller in magnitude here. So note that the RL is the same. And in this case, RE by RL is close to unity. In this case, RE by RL is 1/10. It's because it is 1/10, you get a higher swing here. You get a swing which is 6 volt, But note the price that you have to pay for the higher swing. You're getting a swing which is double as compared to this one. For the same value of load resistance, same supply voltage, everything is same. To get a swing which is double this, what we are having to do is have a bias current which is 25 milliamperes as compared to 3.4 milliamperes. So much higher bias current is required to obtain a larger swing here. And larger bias current, of course, is something that you don't want because the bias current comes from the supply voltage here, and you have a lot of power which you're drawing from the supply. Okay. All right. So it shows, this particular design simulation. If you do it, works fine here. All right. Now, so this is a problem then that we are addressing. The problem is that if you want a swing which is close to the maximum capability of this amplifier, you require a large current here. And we would like to solve this problem. We would like to get a large swing without requiring a very large current. Okay, so that's the problem that we are addressing. So let's look at what is the problem with this particular circuit here. Now, let's look at this diagram here. This diagram we have seen in terms of current driving capability, how swing is limited by that. And we know that swing is limited by negative swing. We saw that in the last lecture here, by the negative side here. Now, if you look at this particular diagram, you note that what happens is this current here is negative because we're talking about negative swing. So it goes up and it comes here. And these two currents add up and give rise to this particular current here. Okay. So basically, this current then has to supply the load current here. Okay. This is the source of the load current here. This is the one which pulls it here. All right. If we look at this current is the net voltage at this point, which is the DC voltage and the AC voltage. AC voltage at this point is negative. So that's why we put V minus V0. That's the net voltage at this node divided by RE. So that's the current flowing down. And this is the current which is flowing up here. V naught by RL here. All right. The negative side is taken care of by pointing the current up here. All right. So this current has to supply this one. Now you can see the trouble with this particular circuit. The trouble is that as I increase my V naught, this current is increasing, right? This current is increasing while this current is decreasing. In fact, you can see what is wrong with the circuit. When I don't want any current in my load, which means V0 is 0. When I don't want any current in my load, here, the current here is maximum. When I want the maximum current in my load here, this current is minimum. So you can see that this circuit, this is the problem with this particular one here. As I'm building up my voltage here, voltage swing here, I require higher and higher current. And on the other hand, the capability of this side becomes lower and lower. The current handling capability of this one here, it keeps on falling. So now the issue is, how do we solve this? How do we solve this particular problem here? So what we want is that the current, what would be the ideal case? The ideal case would be, as I require higher and higher current here, this current becomes higher and higher. Right? That's the ideal case. That when I don't want any current here, the current here in this branch is low. When I want more current here, the current in this branch also rises here. That's the ideal case. What is the next ideal case? Next better case. Because if you can think of an element, so what we are saying is, I want to take this RE out. I want to take this RE out because if I keep RE, this is the situation that I end up with. So RE is not satisfying it's not giving a very good characteristics, the presence of RE here. So I want to take RE out and I want to replace it by something else. Now that something else characteristic should be, as I said, as the current increases here, its current also should increase. That's the ideal situation. If you can think of that element, go ahead and put that particular element here. What is the next best situation? The next best situation, the ideal situation, as I said, is as this increases, the current here also increases. All right. What is the next best solution? As the current increases here, what is the next situation that you can have? Constant current. And the worst situation is as this current increases, this current actually falls, which is where we are right now. So I'm sure all of you are seeing that if I replace RE by a constant current source, that would be better than the solution that we have here. Okay, so that's what we'll do. So the idea is take RE out. It's not a good solution because the current here is falling in response to current here increasing. It's not a good solution. Take this out and replace it by a current source. Because then this current at least is remaining constant. Okay? And so let's do the analysis then with a constant current here. Alright, so this is called a current source biasing here. This was biasing using a resistor, and now we are talking about biasing using a current source here. So we have a current source here. And now you may be wondering what is the role of R1 and R2. If I have a current source here, the role of R1 and R2 is they develop a voltage here and they decide what is the DC value of voltage at this particular point here. Okay, the current in the circuit is decided by IE, and this divider decides what is the bias voltage here. Okay, so if we do that, now look at the situation here. Again, we are talking about this side here. So there's a current which needs to go up, and there's a current here, and then there's a current here. So the current balance is IE, this is the bias current IE equal to V0 by RL, which is this current here, plus the current which is coming from here, IC. And from this equation, we can easily see now IE will always be greater than or equal to V0 by RL, because at the most my collector current, you know, when I apply negative bias here, the collector current is decreasing. At the most, I can make this collector current very close to 0 or negligible. So IE always has to be greater than or equal to V0 by RL, or V0 will always be less than or equal to IE times RL. IE is nothing but the collector current, which is ICQ times RL. So this is the limitation that we get here. V0 is less than or equal to ICQ times RL. So this is the new limitation that we are getting when I bias it using a current source here. Alright, so V0 is less than or equal to ICQ RL, and we'll see the consequences in a minute. The other one is, note the value of VE here. We have to ensure that, you know, this is the DC value here. When I go in the negative part here, the net voltage at this particular point will become VE minus V0. And in general, we'll have to make sure that VE minus V0 is greater than 0. And the reason being is the current source I'll have to implement using a transistor or whatever I'll have to use here. And the net voltage across the transistor obviously has to be greater than VC, SAT, and other things here. Okay, so I'll have to obey this particular condition as well. VE minus V0, the net voltage at this particular point has to be greater than 0 here. Otherwise, ideal current source will of course continue to work, but remember I have to implement the current source using a transistor. And for that to work properly, I have to ensure that the net voltage here remains positive here, at least. Okay, so that's why we have put this constraint here. Alright, so now the following constraint is there. This constraint was VCC minus VB minus VE was coming from here, a usual constraint here. This one is by keeping the node at this point positive always, and this one, and from there these two limitation we find that V0, the maximum V0 that I can get is VCC minus VB by 2. If you just look at these two here, this is telling you that you should make VE as small as possible to get large V0. This is telling you to make VE as large as possible here, and therefore you balance these two limits and you get maximum swing possible in this system is VCC minus VB by 2. And once you get this particular swing, we have to ensure this condition also, V0 less than or equal to ICQ RL, or we need to ensure that we have biased it at ICQ greater than or equal to V0 by RL. We need to ensure that current driving limit is also obeyed, and so that's how we end up getting. So if we look at the design of this particular amplifier, the way the design will proceed is, this particular circuit is capable of giving me swing VCC minus VB by 2. That much swing it will give. So the moment you decide the supply voltage, you know what is the maximum swing possible in this system, which is here. That is possible only if you choose the current in this particular manner. If you choose the current ICQ, which is same as IE, greater than or equal to V0 by RL, then this possible swing is possible in a system like this. Okay, so this is the design criteria. It's very simple. This is the maximum swing, and you have to obey this condition. Okay, and so basically now this is comparing these two circuits here. This one with a resistive biasing here, and this one with the current source biasing here. This I've already said, in order to get large swing, you need to make RE much smaller than RL, and you end up getting ICQ, which is VCC minus VB by 2 RE. And here we've already seen ICQ that you require is V0 divided by RL. V0 is here, so you get this particular one. And you can compare, the two cases here. The current here will turn out to be much smaller than the current over here. Okay, I think I have an example which shows you. Note here, this is the resistive biasing here. This gives you a swing of 6 volt, but requires a biasing current of 25 milliamperes. This also gives you a swing of 6 volt, requires a biasing current of 2.6 milliamperes. All right, and it clearly shows you the superiority of current source biasing here. You need much less current to achieve the same swing as compared to this particular case here. So common collector amplifiers then are regularly built not by resistive biasing here, but by using a current source biasing. Okay. The other problem that you see, so what we have done is we have shown you that from the point of view of swing, getting a large swing without requiring large current, take this resistor out and replace it by a current source here. It makes the circuit much more efficient. The other problem with this particular circuit is, if you look at this one here, we are using a common collector amplifier for several reasons. One is the amplifier has very high input resistance, and the other one is it has very low output resistance here. So if we focus on input resistance here, input resistance is looking from here. As you look right at this particular point here. So as you look right, what you see is these resistors will come in here, which is RB, and then whatever is the resistance looking into the base here. Now, if you look into the base here, what do you see now? Remember, if you look into the base, the net resistance is R pi plus 1 plus beta times RE, right? Now, if you look into the base, what is RE? RE will be equal to, now I have a current source whose small signal resistance is infinity. That infinity comes in parallel with 2.2K. So I have 2.2K here, right? And this 2.2K will get multiplied by beta. Beta is 100. So it will give us 220K. It will give us 220K. Now this 220K is resistance looking here. And it comes in parallel with what? With a very small resistance. And therefore, my Rn is falling to 820 kilo ohm. So you're seeing the trouble. The trouble is that when I look into the base from this side, I actually see a very large resistance, 220K. But then this resistance comes in parallel with this one. And the whole input resistance comes down. So if you're really looking for a large resistance here, what you want to do is eliminate these two resistors altogether. Just eliminate it. All right. If you eliminate 38K and 50K, then what will happen is nothing will come in parallel and you will get a very large resistance here. So that's the motivation for doing this, what you see over here. Note, earlier we had putting R1, R2 and all of that for getting a particular value of voltage here. Now what we have done is eliminated R1, R2 altogether, apply Vs directly. We have a current source biasing, and now note that I need some power here, some voltage here to cause the current to flow, and that's why we put a negative power supply here. The negative power supply is needed to cause this current to flow in this particular loop here. So we've taken R1, R2 out, directly applied the input here, and current source biasing is used, and the load resistance is here. So that's a much better circuit. I'm sure all of you are wondering, how do I make IE? So next, let me show you how you make IE. All right, so look at this circuit again. IE, I'm using transistor as a current source. Now, transistor acts as a current source if I bias it in forward active mode. Okay, so now this IE is taken out, and another transistor Q2 is used to, so this whole thing here is a current source here. So I have Q2, I have this negative power supply here, R1, R2, RE, these are all used to make a current source. Okay, all used to, so you can see this is the familiar circuit here. It's familiar biasing circuit here with the transistor, and it biases it in the forward active mode and causes a constant current to flow. Why constant current? Because it's in forward active mode and there's no signal. There's no AC signal going into Q2, and therefore it's a constant current source here. So this then becomes a better schematic of a common collector amplifier biased through a constant current source. Okay, and so this one will give you, now you can see here, it will give you a very high input resistance here. When you look into this particular node here, you'll see a resistance which is beta times 2K, so you'll get 200 kilo ohm kind of a resistance here. Okay. All right, so that's so from point of view of biasing and getting a large swing, then this is then the preferred mechanism for doing it here by a constant current source here, and one can implement it in this manner. I had hinted earlier that we call this circuit as an amplifier mainly because it doesn't give us a voltage gain but provides us with a power gain here, and we can see very clearly here the power that goes into the taken from the input source is Vs square by 2 Rn here, because Rn is the net resistance seen here. So that's the power that goes that's taken from the source here. Vs square by 2 Rn. Rn is the input resistance. The power that is delivered to the load is V0 square by 2 RL. Obviously, so we are assuming sinusoidal signal here, and we note that V0 is basically equal to Vs. It's a emitter follower. Voltage gain is 1, so V0 is equal to Vs here. And so when we take the ratio, we get Rn by RL. Power gain is Rn by RL here. And we note that Rn for this amplifier will be equal to R pi, beta plus 1 RL. This term most of the time may be much larger here, so we've approximated it by beta RL. So Rn is beta times RL, put it here, and you get power gain which is as large as beta. So output power that is delivered is 100 times, if beta is 100 times larger than Pn. So clearly this is an amplifier here. It has a large power gain, even though voltage gain is less than unity. Where is this power gain coming from? Where is this extra power coming from? From the supply here. The supply is what is supplying all the power here. Okay. All right. So now let's take a. So the formulas are given to you. You have this problem to find out RB and RE to obtain a maximum output voltage swing of 2 volts. Okay. So 10 minutes is the time that you have. So it's a common collector amplifier. There are 2 limits we have talked about. One is coming from the current driving capability. The other is coming from the saturation limit here. And you have to determine RB and RE to get a swing of 2 volt here. Remember, when it's a design problem, in design problem, often there are many solutions. You know, because we are asking you to find out RE and RB. So there can be many solutions because often you don't have enough equations. The equations that are given to you may not be enough to determine a unique answer. You may have to make a choice. All right. You will know that, you know, maybe certain voltage should lie between certain limits, and then you have to make a choice. And sometimes the choice is arbitrary, but go ahead and make a choice. And then on that basis, you'll get the answer. Okay, so let's look at the solution. So the first equation or first constraint on a design is voltage swing has to be less than or equal to ICQ RE parallel RL. So we take this constraint, write it down, ICQ RE RL, RE plus RL must be greater than or equal to 2. And then, you know, as I said, there are multiple ways of doing it. One realizes ICQ times RE is nothing but VE here. So one writes it VE here. 1 plus RE by RL must be greater than or equal to 2. The other constraint is V0 must be less than here. So that tells us that VE must be less than or equal to VCC minus VC sat minus V0 here, which means VE must be less than or equal to 2.8 here. So that's telling you VE has to be less than 2.8. This is telling you VE is greater than or equal to 2. So it's telling you that my emitter voltage has to lie between 2 and 2.8. Right? This is telling you VE is greater than 2 because this 1 plus RE by RL at the most can be 1. So it's greater than 2. This is telling you VE is less than 2.8. Now we don't have another constraint for choosing VE. That's what I said. You have a choice to make here. So this is here. So the choice is arbitrary to some extent, right? So I have to make a choice, and I make a choice of 2.5 because VE has to be greater than 2 here. So 2.5. And once I make a choice of 2.5, then from here, RE turns out to be less than or equal to 25 ohms. And I choose RE equal to 25 ohms. And then ICQ comes out to be, once I choose 2.5, I have RE, I divide it, I get ICQ equal to 0.1 ampere here. And then RB is determined from here, VCC minus 0.7 minus V, ICQ by beta is 1.8K. All right. So there are different ways in which you can do it. There are different ways. I've done it in terms of VE. Somebody may do it in terms of RE by RL, a choice there. It's the same thing. If you make a choice of RE by RL, it fixes a value of VE. Okay. What value you take has to lie between these two. And somebody may take 2.3, somebody may take 2.6, somebody may take 2.2. That's, design always gives you different answers. Yes. Huh? Can you choose 2.8? Yes, you can choose 2.8. All that it says is less than or equal to 2.8. Yeah, you're right. So you can do that. But note, what you'll see is the consequence. If I choose 2.5 here, so remember what happens. You've raised the question, can I choose 2.8? Which means what? Where is this limit coming from? This limit is coming from saturation, which means you're very close to saturation. And little bit of a problem with your circuit in the sense that the resistors have some tolerance. It may cause your transistor to enter into saturation. So you should not be right at either of those limits, either of those extreme limits. That's not a good design. You should be away from here and you should be away from here, from both the limits, right? And now how much away? Well, ideally maybe you should choose somewhere in between, maybe. If you don't have anything, so 2 and 2.8, what is in the middle? 4 point, what will be in the middle? 2.4. Maybe a better choice would have been 2.4. Okay? All right. So that's how you end up getting a design. And so what I did was I took this particular design here with the value of RB, with the value of RE, and I simulated it. I applied 2 volts. I get a nice 2 volt. No problem. So it works fine. And note that when I apply 2.5 here, so I've designed it for 2 volt. When I apply 2.5 volt here, what I get is, obviously it gets clipped here. It gets clipped here because I don't have enough current in my circuit to allow 2.5 volt swing. I had designed it for 2 volt here. So can we modify the design for 2.5 volts? Well, let's see. So we have this constraint as usual from the current limit, and this is the one from saturation. So now for 2.5 volt limit, this one translates into this constraint here, VE by 1 plus RE by RL should be greater than 2.5. While if we substitute V not equal to 2.5 here, the constraint on VE comes out to be VE should be less than or equal to 2.3 here. So now this one is saying VE is larger than 2.5. This one is saying VE is less than 2.3. So obviously a design is not possible. So this particular circuit cannot give me a swing of 2.5 volt here. But suppose one goes ahead and designs. One forgets about this particular one here, this particular limit here, and one goes ahead and chooses, let's say, V equal to 3.5. So obviously I can satisfy this limit. This limit meaning that I'll have enough current in my system, and therefore this limit should not bother me. And suppose we choose V equal to 3.5, we go ahead and use this particular constraint to arrive at a value of RE. So it says RE should be less than or equal to 40 ohms in order to get a swing of 2.5 here. And so we choose RE equal to 40 ohms here. And then based on RE of 40 ohms, we get a current of 88 milliamperes here with V equal to 3.5. And then one can determine the value of RB here. So we have a design here based on only this particular limit here. So suppose we go ahead and build an amplifier with RE equal to 40 ohms, RB equal to 0.914K. then what we expect is that since we satisfy this particular limit here, that on the when my voltage is going to the negative side here, it should not be affected because I have enough current in my system to allow the negative swing here. But while my voltage goes up here, saturation should bother me and my transistor should enter into saturation. So looking at it, what we expect is that maybe the positive swing part will get affected and negative swing would be fine here. So let's see what the simulation results show. So the same particular design was taken, and so we have 40 ohms here, 0.914K here, and upon simulation it gave something interesting. On the positive side it looks fine, it looks like a sinusoid, but on the negative side we see that there's a large clipping here. So the result is opposite to what we had expected. That on the positive side we were thinking that because we were violating this particular constraint that comes from saturation, that we'll have clipping, while on the negative side the transistor has enough current and therefore it should have allowed a proper sinusoid here, but the results are actually opposite. And in order to investigate this, let's go ahead and look at the simulation here. So let me open up my simulator. So we have the circuit here, the same circuit is drawn over here. So let's do a DC analysis here, dynamic DC here. So when we do that, at this particular node we have a voltage of 3.42. We had designed for 3.5, so it's a little bit away from here. And current is 85. We had designed it for about 88 milliamperes of current, so this is there are slight variations here. Anyways, the important point to remember is that we get a voltage of 3.42. This is the bias point here. So let me close this dynamic DC and let me apply a sinusoid here. So I want a swing of 2.5. So let's see what happens. We apply a 2.5 volt sinusoid at a frequency of 1 kilohertz here. So we go ahead and do that, and we run our transient analysis, and we look at the output voltage, the output and the input voltage here, and this is what the result I had shown here. So on the this is the black one is my input curve here, 2.5 volt sinusoid here, and the red one is the output here, and we see that there's no clipping on the positive side, but there's a clipping on the negative side here. So this is a surprising result. We had expected that there should be no clipping on the negative side here, and there should have been clipping on the positive side, but we don't see that here. And obviously the sinusoid is pretty distorted here. And so what is interesting is that because of the distortion, something interesting happens here. Now, what is interesting is that if we go and look at this particular circuit here, as my sinusoid is going and is getting distorted, and as a result of distortion, what we are getting is an additional DC at this particular point here, which is coming about from the sinusoid here. You know, for example, an extreme case of distortion one could think of that, let's say the sinusoid gets half-wave rectified, and we know that a half-wave rectified sinusoid has a large DC component here. So, so what is interesting is if I go and look at this particular node here, this node, and I look at its average value. Now, average value means I'm looking at it is DC value here, and so let's do that. So let's go into transient here. Transient here. Let me go to the limits, and let's look at the average value of that particular node here. And so if I look at the average value here, and let me run the sinusoid for a couple of cycles here. So let's say, let me run it here. And what is very interesting is if we go ahead and look at the average value is 2.65 here. It's going to 2.65 here. Which means, very interestingly, that I had biased it at 3.4 something here, DC value. And then we apply a sinusoid, so we expect the DC to remain the same, and in addition to DC, we expect a sinusoid here. So the average value to remain 3.4. But what we find is that the average value has actually gone to 2.65. So the average value has dropped. So my bias point has really changed. I was expecting it to be 3.5. It has gone to 2.65 here. And as a result of change in the bias point here, now because the voltage has become lower, so I have less current here. And less current means then that I don't have enough current to satisfy a 2.5 volt swing here. And that's why I see clipping in the negative direction here. So this is a interesting circuit, and which predicts that the bias point here at this particular point gets affected by the sinusoid that I apply here. And as I said, if you look at the sinusoid here, it's giving me 2.65 here, and that's because of the AC voltage that I apply here. Now note, I can change the AC voltage here, and we can see the change in the magnitude. Suppose I don't apply 2.5, I apply 2 volt here, AC. I'm not changing anything except for the input voltage here. And let's look at the transient. Now my bias point is 3. It's 3 volt here. And so bias point is changing with the amplitude of the input sinusoid here. And so let me change it further from 2 to, let's say, 1. And now the bias point is very close to 3.4 or so that I had set earlier. It's going towards that particular point here. So I'm doing an average of my voltage at that point is going to 3.4 here. Okay, so let's stop here.